Hi there, so welcome back. So in this new video, what we're going to do is advanced post-processing now using Python. So remember in the previous video, we saved the data along that line, okay, velocity, wall shear stress, and allocation, okay, and then we can use that information to do the plotting. So here, okay, here in the website, you will find the Python notebooks. I will put the link later that you can download everything. But basically what we're going to do, I ask you to install Python, Anaconda Python. So you go here to the startup, as you install that, you will see here that you have the Jupyter notebook Anaconda 3. Okay, launch that one with support to Python 3. Okay, and what is going to happen that you are going to get this window. Okay, in my case, here you need to look for the files, okay, where you have the file, the location where you have the IPython notebooks. So in the files that you download, you will see that, let me go back here, I put it in this location. See here that you're going to find this folder, plots data analysis, and here I already put all the data, all the notebooks. So as you go back into this first one, okay, see here that first this extension IPyNB means the IPython notebook. This is the Python notebook that you open here, okay? So I like to use this one because it's web-based and really easy to understand, and you can publish this, online. So basically these notebooks are reading this data, and see this data, this is the data coming from Fluent. As you recall, Fluent, we were saving the sampling along a line. Okay, so see here that this is the velocity, the line, and the location. Okay, and here you have the wall shear stress. So using this information, wall shear stress as the wall, we can do the plotting outside Fluent. That probably, I think, is the way I prefer. Okay, it's more user friendly and you can do more stuff. So see that, for instance, I know that I have my data located here. You go there and then open your notebook. Okay, so this is the notebook. Okay, so let me close. I already have that at one open, and see here that you have that notebook. Okay, so I already addressed this, I think, in the live lecture, but let me do it again. So this is a web-based Python notebook. Okay, so you can have a clean Python script, or you can put it in this interface. Okay, as I say, it's something that you can share online. Okay, so all the commands that you see in every cell are commands that correspond to Python programming language. Okay, and something similar you do in MATLAB, as you are used to MATLAB. So for instance, you want to run the whole Python notebook. Here you see in cell, run all, and it will run all cells. Okay, so you're running everything. If you want to run a single cell, you need to press Shift Enter, and you run that single cell. Okay. In this case, it's okay to run everything, and let me go through what we're doing. So these are stuff just to do plotting in the web page. You are loading here some libraries. So this is library with numerical analysis routines. This is to do plotting, and here we're loading this data. So load this file. So this is important. Remember, this file is coming from Fluent. So this is the sampling along a line. So you're saving this file, okay? And you are reading that file using these commands, okay? Something important when you are reading this file, I did it just because, just to save steps. When you save this file in Fluent format, Fluent at the end is going to put a parenthesis, erase it, just to read this file straightforward here in Python. Okay, so if you leave this parenthesis, and let me show you here, so let me run this, it will give you this error because that parenthesis is telling you line 87, you see here. So if you erase it, now it will run, okay, with no problem. So you can get your way around in Python to ignore this error. Okay, there is no problem, but just to make things easier, okay, and just I would put it like this. Okay, so later you can find out more about what is happening there. But if you are reading in MATLAB, maybe you're going to have a similar error, maybe not. Okay, just check that, but be careful with that. So now in this one, what I'm doing is computing of this file that you are reading, that you are saving in this array, compute the maximum velocity and the position of that maximum velocity in this array. So it's telling you that your maximum velocity is this, and it's located in that array in the position 40. Okay, I need that one to do some later post-processing. So here, see that we have the power law correlation. Okay, and here we plot the sample velocity, and then also we plot the power law correlation. Okay, so see that these are the commands to plot, okay, there, and this is the power law, okay, that we plotted there. And you can keep reading theoretical profiles. See here that you have the traditional equation, so you create a linear space from 0.1 to 100,000, this many points. Okay, compute U plus, X plus, Y plus, compute the Spalding law. Also see here that you have the equation, this linear space, put it there. Then your global properties, velocity, rho, mu, nu, and then you can compute here. These are the actual values of the simulation, the numerical simulation. So see, this is wall shear stress. So you go back to the data that you save. Let me go back here. WS correspond to this value. So you just put the shear stress at the wall, and then here this is the standard equations. Shear velocity, Y plus, U plus. Okay, so this is the values for the numerical solution, and now here you do the plotting. Okay, so let me run everything. Here you have the plotting. Okay, so this is the mesh. Actually, you see here, this is the sweep mesh. Okay, and you have here your solution. So you have the Spalding law, the viscous layer, and the log law. Okay, and see that this one, this case, have a rather narrow overlap region or logarithmic region. And here you have the viscous layer, the buffer layer. You see this disagreement here. It's a small one. This is not a problem, but this is related to the mesh. You know, we're now in 3D. You need finer mesh, this stuff. Instead, in 2D, we have a very good mashing, okay, but in 3D it's in chance a little bit, because now remember in 3D we have this vortex stretch and all this stuff that we need to take into account, but this is acceptable, okay, for our purposes. So this is how you do the plotting, okay. So we go back here. Remember, in Fluent you just sample velocity and a location, the line normal to that location, get velocity, and then using any program that you like, in my case I'm using Python, do this plotting. Okay, so you can do the plotting velocity, okay, distance, or also you can put here also Y plus, and then compute your theoretical profiles, put it there, and do this plot. Okay, so let me show you now here, for instance, is you go in your data structure now, so you go out from this one, and you go in data plots. You find this plot, laminar this IPython notebook. This one corresponds to this. Okay, so this one will look at the turbulent and laminar solution, and it will do the comparison. So see that it's looking for the information contained in these directories. So see that you go laminar, tn off, where you have this file here. I was just reading this file, that is the file sample from Fluent, just to remind you that here I'm erasing the parentheses at the end just to avoid that error, but you can get your way around using regex notation, whatever. So see that here you read another one here in Turbulent, and this one. Okay, you read that profile and so on. So this is what I'm doing here. Read that, then do the post-processing, compute the theoretical profiles, and do the plotting. So here are also, for the laminar case, I know that I have also the Poiseuille solution, okay, the Hagen-Poiseuille solution. This is the profile. And then you have the power law correlation, and we put it here. So you see that the laminar have a very good agreement with the Hagen solution, Hagen-Poiseuille solution. Okay, then we move in the files in our directory structure, and let me move here. We're in data plots. We open this one. As you go into laminar, then you are going to find another IPython now, but as you open that one, it's just plotting the laminar data. Okay, so see that you have it there, and here you have the comparison also. When you see TN on in your data structures, let me go into that, means that turbulence model on, turbulence model off. And what is mentioned that is you are sure that your data is laminar. There is no reason to run with the turbulence model on, and actually will be slower because you are solving more equations, but also it might add some diffusion. So because that turbulence model is kicking in, is adding that artificial viscosity, that turbulence viscosity, and see here that you see the influence, okay? And then the other one, the final one that you are going to find here, you go into turbulent and you have this plops profile, and as you open that one, see that you're going to have pretty much the same, just accessing the data in a given folder, that you have all your folder structure there, okay? You access your data. Actually, in this case, you don't have folders, you have the text files here. So see that you have all these text files. Here you put your values, okay, for each one. You have your flow properties, compute everything. So then you can browse this. So U tau, Y plus, compute it in the traditional way, and you just do these plops, okay? So see different meshes. This is velocity profile. Then here, this is for the mesh. Compute Spalding law, all that stuff, and you plot here wall resolving and wall function. As I mentioned, that wall function, see that you put your first node far from the wall, okay? So this is about 100, and you are saving all those cells here, okay? And they work remarkably well. So see here that we're close to this logarithmic law there, so they work very well, okay? So you have their plot there, and then in this one we compare the compressible solution with the incompressible one, okay? So remember that in the compressible one now we have actual density, viscosity values, larger velocity, but disregarding that, we should always reproduce this profile that you see that we have it there, okay? So you have all these notebooks here, so you can see how to reproduce the data, how to do this. This is basic verification. So this is something that you do when you are completely lost. You know what you are doing with a new case. So you try to reproduce these plots and you manage to recover this profile. You know that you are doing you are on the right track. Okay, so this is all for this case. Okay, and the last case, the last video that I'm going to prepare is just to show you how to do this. So see that this is the incompressible case, but also we're running the compressible case, this one. So just to show you how to set up the same case turbulence model, but using this the compressible model, okay? And then also I'm going to show you how to do these plots as well. We already did it in 2D, but also just to revisit again how to do it within Fluent, okay? So those will be the last videos. Okay, that's all for the time. Okay, thank you for your attention. See you next video. Bye.